Hey everyone and welcome. Today we are diving deep into the incredible world of carboxylic acids. Now you might not realize it, but these molecules are literally everywhere, from the clothes on your back to the food on your plate. Understanding how they react is going to unlock a huge piece of the organic chemistry puzzle. So let's get right into it. Okay, so first up, a quick question for you. Just think for a second about the tough fibers in a nylon jacket, the amazing scents in a bottle of perfume, and, the preservatives that keep our food from going bad. They seem totally unrelated, don't they? Well, what if I told you they all share a secret chemical ingredient? Yep, you guessed it. The common thread is the carboxylic acid. Hexanidolic acid is absolutely essential for making nylon 6.6. The esters of benzoic acid are the stars of the show in perfumery. And sodium benzoate, that's a super common food preservative. These molecules are pretty much the unsung heroes of our modern world. And today, we're going to figure out exactly how they tick. So how do we even begin to make sense of all their different reactions? Well, the secret, and this is the absolute key to everything that follows, is to think of the molecules having two distinct personalities, two different zones where all the action happens. This slide breaks it down for us perfectly. Just imagine splitting the molecule right in two. Over on the right, in pink, you've got territory 1. That's the main functional group, the carboxyl group, the good old COOH. This is where a ton of the chemistry happens. And on the left, in green, that's territory 2, the hydrocarbon part of the molecule. Each of these territories has its own unique set of rules and its own special reactions. All right, let's start our journey in territory 1. For the next little bit, we're going to focus only on the reactions that happen right on the carboxyl group itself. Okay, one of the most fundamental transformations you can do is called reduction. This just means we're going to take that RCOOH group and convert it all the way down into what's called a primary alcohol, an RCH2OH. But to pull this off, you absolutely need the right tool for the job. Think of it like a choose-your-fighter screen in a video game. In this corner, you've got lithium aluminum hydride, or LiAlH4. This is your heavy hitter, your chemical sledgehammer. It's strong, it's reliable, it gets the job done. Then you've got diborane, or B2H6. Now this one's the superior choice. It's more like a surgeon's scalpel. It's so precise it can reduce the carboxylic group while leaving other things like esters totally untouched. And then there's sodium borhydride, NaBH4. For this particular fight, it's a no-go. It just doesn't have the muscle to reduce a carboxylic group at all. So what if you don't want to just change the group, but get rid of it completely? Well, that's where decarboxylation comes in. You use a little soda lime, which is just a mix of sodium hydroxide and calcium oxide. You add some heat, and you can basically just pop off that carboxyl group as carbon dioxide gas, leaving you with a plain old hydrocarbon. But get this, there's a really cool twist. A reaction called Kolbe electrolysis also removes the group, but then it takes the leftover alkyl part and fuses it to another one, giving you a hydrocarbon with exactly double the number of carbons you started with. How cool is that? All right, we've explored territory 1 pretty thoroughly. Now it's time to cross that dotted line and head over into territory 2, the hydrocarbon part of the molecule. And trust me, the rules are completely different over here. The first major reaction in this neighborhood is the Hell-Volhard-Zelinsky reaction. Yeah, it's a mouthful, so we just call it the HVZ reaction for short. Now look closely at the diagram here. The target is super specific. It's the hydrogen on the carbon that's right next to the carboxyl group. We call that the alpha carbon. The HVZ reaction uses red phosphorus and a halogen, like chlorine or bromine, to swap out that one specific alpha hydrogen for a halogen atom. Okay, so that's what happens on a straight chain. But what if our hydrocarbon part isn't a chain at all? What if it's a benzene ring, making it an aromatic carboxylic acid? Do the same rules even apply? Not a chance. When it's attached to a ring, the carboxyl group gets this new superpower. It becomes a strong deactivating group, which basically means it makes the ring a little lazy, less eager to react. But even more importantly, it's exclusively meta-directing. As you can see on the slide, you can think of it like a chemical umbrella. It shields the spots right next to it, the ortho and para positions, and forces any new group that comes along to attach only at the meta position, way on the other side of the ring. And we can see this rule playing out perfectly in these two classic reactions. If you do a nitration reaction with nitric and sulfuric acids, that nitro group, the NO2, doesn't just go wherever it wants. Nope, it's directed to attach right at the meta position. It's the same exact story with bromination. The bromine atom gets steered squarely into that meta spot, all because the carboxyl group is calling the shots.
So this meta-directing rule seems pretty solid, right? Like it's a hard and fast rule. But does it work for every single type of ring reaction? You might be wondering, hey, what about the famous Friedel-Crafts reactions?
And that is a fantastic question, because those reactions are the one major exception. Friedel-Crafts reactions simply do not work on aromatic carboxylic acids. They just fail. And there are two big reasons for this. First, like we said, the carboxyl group is just too deactivating. But the real knockout punch is this. The catalyst, in this case a Lewis acid like aluminum chloride, which is basically a molecule that's hungry for electrons, it gets stuck. Instead of helping the reaction happen on the ring, it just bonds directly to the oxygen on the carboxyl group, and that shuts the whole process down.
Okay, we've covered the reactions in both territories. For our final section, let's switch gears and tackle a slightly different question. What determines the strength of a carboxylic acid? Why are some of them more acidic than others?
This slide lays out the rules for us beautifully. It really all boils down to what's attached to the rest of the molecule. An electron withdrawing group, like fluorine, acts like a tiny vacuum, pulling electron density away and making the acid stronger. The more electronegative that halogen is, the stronger the acid, so fluorine always beats chlorine. And proximity matters too. The closer that withdrawing group is to the COOH, the bigger the effect. And finally, on a ring, electron withdrawing groups make the acid stronger, while electron donating groups do the opposite. They make it weaker.
Phew! We have covered a lot of ground. Reduction, decarboxylation, halogenation, ring substitution, the works. Now let's tie it all together into one single unified picture.
And as we pull all these threads together, it's really worth remembering why this chemistry is so important. I mean, from industrial solvents like vinegar to the very foundation of soaps and detergents, these reactions aren't just abstract ideas in a textbook, they are quite literally the building blocks of the world around us.
And here it is, the carboxylic acid reaction web. This is your ultimate takeaway. You can see our starting molecule right there in the center, and from there, you can trace all the paths we've learned about. Follow the arrow to reduce it to a primary alcohol, pop off the CO2 to make a hydrocarbon, use HVZ to make an alpha halo acid, or substitute the ring to get a meta-substituted product. See? It all connects.
So we've cracked the code of the two territories, and they're totally different rules. We've seen how to transform these molecules and why they are so vital to, well, pretty much everything. The only question left is, now that you know the playbook, what new and amazing molecules could you design?